ATC-2021 virtually. My name is Stanley Zhang, and I'm from King's Distributed Systems in Canada. Today, we are presenting chest X-ray abnormalities localization via Ensemble of deep convolutional neural networks, alongside co-authors Van Tien, Gongming, Jiming, and Shan Danu. The field of computer-aided diagnosis has significantly expanded in the last few years. This is due to the release of high-quality, large datasets and improvement in state-of-the-art computer vision modeling. Today, we present a convolutional neural network deep learning framework for chest X-ray interpretation. What exactly does this all mean? We are presented with a chest radiograph, or X-ray, and we must localize abnormalities. For example, pneumothorax, pulmonary fibrosis, or lactasis. Our framework must identify these diseases, as well as identify normal chest radiographs. Then, we must localize these abnormalities, which means to place a bounding box over the area identified as abnormal. In this case, pneumothorax in red and lactasis in blue. Our work is based on VinDr-CXR X-ray, a self-described, quote, open dataset of chest X-rays with radiologist annotations, end quote. There are 15,000 train images, which were each labeled independently by 3 radiologists. With the 3,000 test images, a consensus of 5 radiologists was used. Each image has localizations, and since each of the training images have 3 sets of individual labels, a little bit of a problem is presented with this. And we'll be discussing this problem further later. Let's first learn how we are evaluating everything. Mean average precision at an intersection over union threshold of 0.4, abbreviated as MAP 0.4. I'll call it MAP for the rest of this presentation. MAP is an object detection metric, and it works as follows. You may be familiar with the metric precision in classical classification tasks. It is defined as the number of true positive predictions divided by the sum of the number of true positive predictions and false positive predictions. So for an object detection task, we are not only classifying, but also localizing abnormalities. So how can we frame these true positives and false positives differently to fit our task? This is done with intersection over union, or IOU. Here, we see 2 bounding boxes overlapping. One of them being the ground truth target from the original dataset, and the second being one predicted from a model. IOU is defined as the area of the overlap divided by the area of union. If IOU is above 0.4, then it is counted as a true positive. Else, our bounding box is counted as a false positive. Then, mean average precision is just the average of the precision at as a specified intersection over union. We average the precision at that given intersection over union for every individual class. And as with precision, a higher MAP is better. Next, let's explore our paper's main contributions. VinDr-CXR X-ray has a few core problems for us to solve. Firstly, we have 14 abnormal disease classes and 1 normal class. The normal class is global, meaning it spans the entire image and is exclusive with all abnormal classes. And of course, we want to minimize false positives. Instead of feeding chest radiographs directly to our object detector model, we first use a 2-class classifier filtering model. For this paper, we use 2 model architectures that are the de facto standard for classification, which are ResNet, specifically ResNet 50, and EfficientNet, which are previous state-of-the-art models and extremely fast. The classifiers are trained on 2 classes only: chest radiographs containing 1 or more abnormalities, and chest radiographs with no abnormality. Positioning and abnormality are dropped. This model solely differentiates which images to pass on to the object detector models. This model also is trained on external datasets, namely chest X-ray 14 and pad chest, which were unified into a single dataset. The 2-class classifier scheme also has a secondary benefit aside from reducing false positives. Since the classifier narrows down the chest radiographs that must be inferenced by the slower object detection models, it's a little bit faster. For example, in the training dataset, there are 4,394 images with abnormalities out of a total of 15,000. This means we can filter out nearly 2/3 of chest radiographs. Our second stage is 3 object detector models seen here. Faster recognition-based convolutional neural networks, also called faster RCNN. You only look once version 5, also known as YOLO v5, and EfficientNet. These were chosen for their speed and are all current state-of-the-art models on different given datasets. Each detector was trained solely on images containing abnormalities, since our 2-class filter would filter out all of the images without abnormalities. After inference on these three detectors, we're given three sets of labels. And of course, we don't want to use all three sets of labels in our final prediction, because we would just be given excessive false positives, which are not desirable. Instead, we need some method to combine labels based on their class, confidence, and of course, location in relation to other bounding boxes. That's radiograph. And to do this, there are three main methods of ensembling our multiple predictions. First of all, non-maximum suppression, weighted non-maximal suppression, also called non-maximum weighted, and more recently, weighted boxes fusion. I'm not going to go through the algorithms for each of these, but the gist is that non-maximal suppression tends to choose the most likely bounding box out of the group given, while weighted boxes fusion tends to average the given bounding boxes. We determined that weighted boxes fusion that was the most performant for our task of ensembling our model's predictions. So that pretty much covers our modeling framework as a whole. Next, we'll discuss some techniques used in training. Here's an overall summary. First, let's look in EDA to understand some of the motivation for our choices. I mentioned that one of the features of VinDr chest X-ray is that it has three separate label sets, one from each radiologist. So firstly, we must ensemble the labels into one set to train on by applying weighted boxes fusion to the training labels. The left chest radiograph is the original X-ray labeled by three separate radiologists, so it's rather messy. Then our output after the weighted boxes fusion is on the right, which is significantly cleaner. Let's take a look at a few graphs. First of all, we observe a significant label imbalance within the annotations of abnormal chest radiographs. As such, we desire an even distribution of labels across our validation. We use multi-label stratified k-folds based on the abnormal labels in order to validate our model. We can also consider using a class-aware sampler, such as synthetic minority oversampling, also known as SMOT, but we also didn't see a huge performance uplift in that to justify the computation. This next visualization shows which radiologist annotated which images. There's another clear imbalance, but since we don't have access to such data in test time, we did not use this. Finally, and most importantly, here's a heat map showing the average position and area covered of each bounding box by class. For the first one, we have the average of all abnormal classes. Aortic. For the second one, we have aortic enlargement, etc. And we can immediately observe significant biases in all of these. For example, in the top row, second from the left, we can see the average bounding box prediction for aortic enlargement. It's significantly biased to that particular area in the top left of the radiograph, where the heart normally is. Since the aortic enlargement, since it is aortic enlargement, this does make sense since it is a disease of the heart, but it also provides a problem from a modeling standpoint, as it introduces significant bias and cannot always be assumed that the location of the heart will be exactly in that area, as different chest radiography machines and patient positioning are possible. As a result, we introduce rather radical augmentations to reduce the bias of our model and improve generalization. We utilize Albumentations, a Python library containing a multitude of augmentations. We use these to diversify data, avoid overfitting, and mitigate the label imbalance. We use augmentations such as shift, Gaussian blur, color, contrast, hue shift, channel shuffle, and mix-up. This is a visualization of 8 individual images that were trained on. As you can see, the augmentations are fairly major. No longer are labels associated with particular areas of the image, but rather scattered, as the augmentations shift the chest radiograph around the image. So after combining all we have discussed, we arrive at the following, which is our testing scheme. Given a chest radiograph, we first utilize our two-class classifier, whether the ResNet 50 or the efficient net, and classify it. If an image has no abnormal finding, then our modeling ends here. It has no abnormal finding after all. If it has an abnormal finding, then we select a detector or ensemble all 3 of the detectors to localize abnormalities. Finally, we ensemble these detectors using weighted boxes fusion into our final bounding box output. Let's look at our results and findings. First of all, we see that for every model but one, efficient net, the two-class classifier improves performance on MAP at 0.4. We speculate this is since efficient det uses efficient net as its backbone, and therefore a ResNet 50 based two-class classifier brought greater diversity to the scheme, and therefore better performance. There is a very detailed analysis of performance and of this graph on the paper. In interest of time, we found the fastest detector to be YOLO V5 at 20 frames per second, and efficient det to be the slowest at 9 frames per second. Our best score was with an ensemble of detectors, adding EfficientNet B7 as a 2-class classifier, which elevates the score from 0.272 with only the ensemble of 3 detectors to a mean average precision of 0.292, including EfficientNet 7. Inference time is also a crucial metric in high-volume cases. For example, a hospital adopting a new computer vision technology on an existing massive database of chest x-rays, or perhaps in times of great need and emergency, say during COVID-19. So after all of this, why trust our scores? How are our scores real? The test set for VinDr-CXR x-ray is withheld, meaning that we must submit our models in order for them to be evaluated. In this case, we submit our code to Kaggle for evaluation on their servers. Our model produces predictions on images, and they are evaluated completely by Kaggle. All of the previous mean average prediction scores were scored this way. We locally cross-validate using stratified k-folds to select models, but our final findings are presented with this official score. Overall, in summary, this research highlighted the importance of solving the class imbalance problem when working with VinDr x-ray, one of the latest high-quality datasets. A proposed framework with a combination of 3 classifier options and 4 model detectors were tested and cross-validated with the test dataset. The 2-class classifier and ensemble technique for the detector model is highly recommended for further study, since the combination presented the best mean average precision of 0.292. The computing time and system performance are also analyzed for a well-rounded consideration when applying different chest x-ray diagnosis situations. Code is at GitHub in our paper. This entire pipeline is inference ready, taking in DICOM post-anterior chest radiographs, and runs on any CUDA-enabled GPU with over 3.5 gigabytes of VRAM. We also have many other proposed pipelines in the paper for optimized speed or other use cases, so please do see our paper. If you'd like to take a look at our code and submissions without running them on your own machine, mainly for experimental purposes, we have a demo notebook at bit.ly/cxr-abnormalities. That's chest x-ray abnormalities. With a Kaggle account, it will be run completely on their GPUs, requiring no local hardware. Thank you so much for attending our talk. If you're interested in reading the full research paper, please have a look at our paper, Chest X-rays, Abnormalities, Localization, via Ensemble of Deep Convolutional Neural Networks, and feel free to contact me at stanley@kingsd's.network. That's stanley@kingsd's.network, or any of my other co-authors listed in the paper. Thanks again, and goodbye.